Hello, world.
Should we start our own VMs? Should we all start our VMs?
By all means. This isn't so much a VM as a machine that is less underpowered than the netbook I normally carry around with me. This netbook has many hours of battery life, it's extremely portable, and it's powered by a wind-up toy. So if I actually do test builds for you, we'd be here a while. All right, I pretty much am forced to start. Let me see, did I decide to go with index or index 2? Yeah, I think index 2. Yeah, 6 of one, half dozen of the other. I'm pretty much forced to start with the concept of circular dependencies. When you are building a Linux system, if you've ever installed things, there are often other prerequisite packages. Well, when you get down far enough, the dependencies become circular. You can't install a system without boot media, a USB or CD to boot it from. You can't create a boot media without having a running system. You know, way back in the dark ages, we had punch cards and paper tape that you could physically write information to, or the switches on the front of the Altair that you could flip. Here's the address. Here's the value. The write button, and you could literally toggle in a program if you had hours to do it. That went away a long time ago. We now have millions of bytes of stuff. And when you're putting together a system, something you're going to hit a lot, especially if you ever deal with something like Linux from scratch, is you have to build packages before you can build other packages. And in order to avoid bits of the host system leaking into the target, you sometimes have to build something that you're not actually going to install, but you're going to build against. So we'll get to all that. But the reason I introduce with the concept of circular dependencies is I have spent 2 weeks attempting to come up with a nice linear index of, here's the topics I want to cover in this order. And it's circular dependencies all the way down. So we're going to be explaining some stuff and then coming back to explain why that was incomplete or wrong a little later. All right, so circular dependencies. So there are four basic components of a build environment, of a Linux system that's capable of rebuilding itself under itself from source code. Those four are a kernel, a C library, a set of command line utilities, and a toolchain. And a toolchain is what all the embedded geeks call a compiler and linker and the make program, the set of build utilities that actually let you compile stuff. When you are creating a system, though, it doesn't have to be able to rebuild itself under itself. Your tiny little embedded ones generally don't. So your build time packages and your runtime packages, one of the ways that you break circular dependencies is by separating them. Okay? One of the things I did as backstory to this a long time ago is, starting like 15 years ago, I created a project called Aboriginal Linux, from the Latin ab origine, from the beginning, where basically I started with Linux from scratch and I went, okay, what is the smallest, simplest build environment I can get capable of building itself from source code? Those 4 packages I talked about are conceptual packages. I got it down to 7 actual packages, which were the Linux kernel, uclibc at the time, make, bash, binutils, gcc, and I list them here, and busybox. And in order to make that work, I wound up actually maintaining busybox for a while because I did so much work with, if I want to replace the GNU version of sed with busybox sed, it didn't work. So I upgraded it to the point where, I upgraded their sort command, I upgraded their mount command, and it got to the point where the previous maintainer just handed it off to me for a couple of years, and then I handed it off to Dennis Vlasenko. But busybox has had a lot of work over the years to make it provide the set of command line utilities all in one package. And that was an explicit goal. That took years of work. The others, the toolchain I used at the time was binutils plus GCC plus make, so 3 packages there. And by the way, even busybox, at the time I was substituting in bash for its shell because I never got around to upgrading its shell. That's why there's a 7th package there. Busybox has had some work on its shell since then, and it's possible that you could build Linux from scratch with busybox ash these days. I haven't tried it recently. This was an old version of GCC that had binutils and GCC as 2 packages. Now they've metastasized to 5 packages. So the simplest system with modern packages is less simple than previous systems were. Fun stuff. Linux is still Linux. For a while, Linux needed Perl to build because Peter Anvin decided that was a thing in 2625. And it took me several years of submitting patches to remove Perl as a build requirement before that finally went away in like 2013. Okay, so let me start by the simplest thing you can do to boot a system is because I'm in the wrong. Let's see. Yeah, I have it in the intro file. No. Okay, so how simple can we get? Here is a page where someone booted Hello World on the bare metal. Okay, and you can easily Google for this, or you can go to that URL. I'll post a list of the URLs I went to after the talk. But basically what he did is he has a little function that just repeatedly writes to the output register of the serial port and has that iterate through a string, and then specially builds it with a little assembly header and with a linker script that puts stuff in the right place, does this stuff, which, the assembler, GCC for the C part, linker running the special linker script, and then a program called objcopy that takes it from the ELF format and copies it to a binary. It basically, the ELF format is a bit like zip or like tar. It's an archive format for storing executable data. So there's a variant of ELF that stores shared libraries. There's a variant of ELF that stores dynamically linked programs. There's a variant of ELF that stores statically linked programs. It's basically the same archive with different header information. And what this does is this extracts just the raw binary blob, output format binary, and puts it to test.bin. And one of the things I did is hello hardware make.sh. The other thing I have to introduce is the concept of cross-compilers. We'll get to that. I mentioned circular dependencies. And so if I run make.sh, which I ran on that machine, and the paths are different, of course. Let's make MCM2. Ha, there I have it. So this is actually the machine I also cross-make. MCM2 output. Let's try that now. Hey, so that just compiled the program and created a test.bin. And then run is copied from his thing, where we call QEMU system ARM, tell it machine versatile PB is one of the ARM systems QEMU knows to emulate. Does anybody here not know what QEMU is? Okay. QEMU is an emulator. It's a program that creates a virtual machine and runs the code you feed into it. It has a built-in bootloader, where basically it can go this file, copy it into the virtual memory, and jump to the start of it. You know, if it's in a known format, it can actually read the header on it and go, oh, this is an ELF file. I'll do basically what objcopy did, copying into memory myself, and jump to the start information out of the header. Here we already did the objcopy, so you know the bare metal one. The -kernel test.bin argument is basically telling it, use your built-in bootloader to load this into the virtual machine's memory. -nographic says, instead of popping up a window with the bitmap output of your emulated video card, you know, whatever the program that's running wrote into the, you know, it tried to access the emulated hardware and its driver intercepted that and wrote it into the window. Instead of doing that, just have a serial port on the standard in and standard out of the QEMU program, so that whatever you write to QEMU's standard in goes to the serial port, and whatever the serial port, you know, whatever the program writes back to the serial port goes to standard out of QEMU, so that you can actually, you know, interact with it on QEMU's standard in. And you can actually do things like use Tickle to script emulator instances that way. It's very useful. The -M128M says 128 megabytes of memory is how much should be installed into the virtual machine. This says basically what motherboard to emulate. What board? Board is shorthand for motherboard. It basically says put this processor in, put memory at this location. All the information about, you know, all the information that would be in device tree when we get to that. You know, all the information that the kernel needs to know where to look for these devices, well, QEMU similarly needs to know where to put the emulated versions of them. So we told it this is a common type of very old ARM board from, I think, the 90s, the ARM Versal board. And then this is just me telling it, don't attempt to emulate an audio device, because if you do, it will spam standard out with a bunch of, I failed to connect to OSS. And it's like, I just don't want that. So when I do that, I get hello world. It booted a virtual system, which wrote something to the serial port and then just spun. Okay? So this is about the simplest thing you can get a machine to do and actually see the output. And my fan is starting up because it is spinning. You'll notice there's a CPU pinned. And the other fun thing about this is we're now going to tell you why it's wrong. And the reason that it's wrong is, oh, come on, I have it in here somewhere. The reason that it's wrong is that real serial hardware only works at a certain rate. You know, it has a UART buffer that can fill up. If you just spin writing to its output register, it's going to start discarding data fairly quickly. What you need to do is you need to read a status register that will have a bit set that says, I am ready for the next byte or not. And you can actually fetch that out of the Linux kernel source code in, it's under drivers, yeah, TTY, serial, amba pl 011.c, and then put console put character. It's doing a read from a register and anding it, and while it's doing that, you know, CPU relax is basically a way of telling the processor not to overheat. It's a no-op that takes a little extra time. And then write the character once it frees up. So you note that a driver attempting to talk to real hardware is doing an extra step that the emulator is not doing. And we're going to hit that a few times in here. But the really fun thing about this PL 011 console put care is a Linux driver that's designed to work before interrupts have been enabled, early in the Linux boot process, early print K. We'll get to configuring the kernel in a little bit. And that means that before Linux has really initialized most of the other hardware, it may want to print stuff out very, very early on. Which means if you know what your serial hardware is and where it's configured, you can basically look up what these macros are and substitute in the constants and cut and paste a line or two that let you stick print statements into anywhere. You can stick it into a bootloader, you can stick it into early boot. You can truly debug almost anything with print statements. You know? So that's actually a nice little technique to have in your back pocket, and we will get back to that. So, the other thing that's wrong with that is we're doing the simplest possible Linux system, and clearly Hello World is not Linux. So let's actually do what it says on the tin. And I should have done that beforehand, because I want to build 410. And I don't know how slow the net here is going to be too slow. All right. Can you give me 4.9? I don't know when the last time I did a poll on this machine was. All right. So the other thing, other than circular dependencies, is we're going to have to define simplest. What I'm going to show you right now is the simplest way to build a Linux system. Hello? What are you doing? Where are you at? Random thing in 2016. Oh. Right. Lovely. Do I have any others? I have a bunch of others. Well, here's 3.5. Right. Sure. That's ancient. Still works the same way, though. Did you finish? Yeah. What? The downside of switching to a much faster machine right before the thing is my careful setup I ran through is right there. Yes? The 4.9. 4.9. There we go. All right. So it's going to boil down to, we're going to do a, yes. Which of the, yes, I know. All right. Did I put it in here? Sure. Okay, the theory behind building a kernel always boils down to you're going to do a make config, you're going to do a make, and then you install and boot the result. A lot of the times we're going to be cross-compiling. The difference between native compiling and cross-compiling is something that I'm going to explain. On an x86-64 system, we're going to start with the available def config. So if you go make help grep _ def config, it should list for the architecture you've selected the available. Are you still checking out? No, you're not. Come on. There we go. So it has i386 def config, which is 32-bit, and x86 64 def config, which is 64-bit. If I selected a different architecture, there's a bunch of architectures in the Arch directory. If I selected, make Arch equals ARM, I'm going to get a whole bunch of def configs. But for right now, the simplest way of doing it is to build for the same architecture as this thing, to not deal with cross-compiling at all first. And I'm going to go make x86 64 def config. That's an underscore there. I don't think you can actually see it. Seriously?
Yeah.
Ah. There we go. And then make -J8 as soon as we're done. Come on. You can do it. make J8. And this is going to build an awful lot of kernel. And that's going to go for a while. So meanwhile, in another window, the reason I opened the second window, let's build a hello world binary. So the reason for this instead of exiting is that I'm going to run this as PID 1. When a kernel boots, it needs a bootloader to have run to load it into memory. And there's a couple of times that it can run straight around, but we'll get to that. Then the kernel needs to know the board layout, where to find the physical memory, where to find the serial port if you're using a serial console, where to find the I/O devices. Even if you have buses you can scan, you need to know what buses there are and where to find them. So it needs some starting data before it can even scan the rest of the system to see, what's plugged into USB. Well, where's the USB controller? And then it needs a root file system in order to load its first program from. And it needs the first program to run. And we're going to provide all those things in the little system we put together here. We are going to use an initramfs, and we are going to use a statically linked hello world program as init. And we're going to boot this under QEMU so that you can see basically hello world run in a different context. So this is a second layer of useless before we start getting to actual useful. Now you'll notice this is building at a reasonable clip. This is an 8-way SMP machine, and it's still building quite a lot. The thing about defconfig is it's got how many symbols? So that's 1164 that are just set to Y. Actually, okay, there's the number that are set. So 1,252 symbols, which select a lot of stuff. We're not going over all of these symbols. We do not have time. So what we're going to do instead, so make defconfig is simple to build. It is not going to result in the simplest system. I thought it would take less time than this. And then to package this up, we are going to do this little invocation. Find period to cpio.o-h newc, pipe it to gzip. And we're going to do that in the directory that has our new root file system. So gzip, I don't actually need the parentheses, and then redirect that to the directory above this, root.cpio.gz. So this has created, I didn't strip that. That's statically linked against glibc, which means it's flippin' enormous. And it even has the source code in there, but that won't bother us. When the Linux kernel boots, it starts by mounting a root file system. There are a couple of ways you can specify where the root file system lives. You can statically link in a CPIO archive into the kernel binary, which will be extracted into memory in a file system called initramfs. Initramfs is an instance of either ramfs or tempfs in more recent ones. Here. Documentation, file systems. Years ago, I wrote documentation on this, so if you want to read through all that, this is just the very quick summary. CPIO is an older archive format that predates tar but still works just fine. They used it because it's simpler. Tar is actually a lot more complicated under the covers. That gets extracted into ramfs. Ramfs is a RAM-based file system. There's 4 kinds of file systems. There's block-backed, which is the conventional ones you're familiar with, like ext2. There's a block device, which is a fixed amount of storage that gets formatted and interpreted through a second driver that tells it what kind of file system there is. There's pipe-backed, which are called different things. Sometimes you hear them as network file systems. Fuse is another example of this, where basically you're talking through a pipe to another program that speaks a protocol, and that other program is providing your file system. So that program may be Samba, that program may be, there's a bunch of things it could be. Pipe-backed ones don't have to be network file systems, but people usually think of that. The point is that it's a serial protocol. The third kind are the RAM-backed file systems, where your files are stored in memory, where basically the Linux disk cache, the page cache, and the de-entry cache that store copies of the copies of file data on their way to whatever backing store there is, because if you're writing faster or if you've read them in and it doesn't want to redo the transaction with either the block device or the server, the cache storing the data in the case of RAM-backed file systems has been plugged so that there's nowhere to flush the pages to. When you write data into a RAM-based file system, there's 2 instances of them. There's ramfs and tempfs in the kernel. When you write it in there, it has nowhere to go, so it stays. And when you delete the files out of them, it frees up the memory so that they automatically resize themselves to how much is actually being used. Now, note that the older RAM disk that you've probably heard of isn't actually a RAM-based file system. It is a block-backed file system where you have a device driver that turns a block of memory into a block device. It exposes it in dev as /dev/ram0 or something like that. And then you use a second driver as the, ext2 or vfat or something like that as the lens you look at that block of memory through. You run a formatting program on it to put it in the right format. You copy files into it, and then you look at it through a second driver. That is a block-based file system, not a RAM-based file system. So a lot of people to this day still confuse those. RAM-based file systems are actually a lot more memory efficient. Because the thing about a block-based file system is you've got the copy in the block device, and then you've got another copy in the page cache. So it actually, it's actually less memory efficient to use the older format. And a lot of people still don't understand the difference between those. The fourth kind is synthetic file systems, where there is no backing store. When you read files or you write files, you're talking to a driver that can do arbitrary stuff with them. Proc is an example of this. sysfs is an example of this. The contents of proc are just hallucinated by the driver. It makes it up. And then when you write stuff into there, it can call any arbitrary function in the driver to do anything it wants. So those are actually 4 different categories of file system. And generally, when you are telling the kernel, when the kernel is booting, it can extract a CPIO archive into the ramfs instance it already has, and this is called initramfs. The older way of doing it, before Linux implemented any RAM-based file systems, it only had initrd, the initial RAM disk, the block-backed version. So it could allocate a RAM block disk and take something like an ext2 image and copy it in there. It could take a gzipped ext2 image the same way that you'd take an ISO image, for example, that you ripped from a CD, and then you can gzip it. Well, you could copy that into the RAM disk and mount it using the ISO 9660 driver as the lens you look at it through. And then the third thing it can do is if you didn't provide either of these two, or if you did provide them but it couldn't find an init program to run out of them, in initramfs it looks for a file /init. It looks for a file init in the top level directory that has the executable bit set. If it can exec that, it'll stop looking further and it'll just launch PID1. In the older ramdisk-based one, it looked for a different name, linuxrc, which is just historical interest. Don't go there. And in init main.c, in the Linux kernel source code in init main.c, there's a function start kernel. So if you go into the Linux kernel source code and look in init/main.c function start kernel, you can actually trace through how the Linux kernel starts up, because this is the one that actually does it. It has a bunch of different places it looks as fallbacks. It looks for sbin init, it looks for etc init, it looks for bin init, and if it can't find any of those, it'll launch bin sh. This is for the third place it looks, if there is a root equals argument on the command line, it goes, this is a block device, mount it, and then try to find an init program in there. That used to be, that's the fallback root file system. So those are the three different places that you can tell the Linux kernel, here's where to find your root file system, and then within that file system you have an init program. So the kernel has finished building, and at the top level there's a file here called VM Linux. This is an ELF program, and I mentioned that ELF is an archive format, and you saw that objdump trick. Well, they do a variant of that objdump trick and then stick a little header on the front to create arch *boot. The file arch x86 boot bzimage. And you'll notice I mentioned that this one's enormous. We're going to go into kernel configuration stuff after this. So what we do is we go QEMU. Let me see. I did a yeah. So, this little trick here, make-j $parentheses nproc. There's an nproc command that tells you how many processors this machine has. So if you want to automatically do SMP at the level that this machine does, you can just, that says run a command and turn its output into an argument. So make-j nproc will automatically do make-j however many processors are in the machine. That's what that little trick does. It's a fun thing. So we did the make-config, we did the make, and then this is kernel command line, which is similar to the bare metal one. QEMU system i386 instead of ARM this time, because I'm running an x86 laptop. -no graphic is the same. Don't pop up a window. Instead, give me a serial console on standard in and standard out. -no reboot says when the system in here tries to reboot the hardware, just exit QEMU instead, rather than restarting it. Here is where that kernel image we just built lives. -initrd of a file. Initrd is, as I mentioned, there's the older boot mechanism that did initial RAM disks. I mentioned that you can statically link a CPIO image into the kernel at build time. Well, the method of having the bootloader point it at an initial RAM disk image that usually was a compressed block device, bootloaders still know how to do that, and the kernel still knows how to listen for that. But what it does these days is first it checks the type to see, is that a CPIO signature at the start instead of ext2 or something like that. If it identifies that you've fed it a compressed CPIO image, it goes, oh, I'll just extract this into initramfs and use initramfs instead of initrd. So it can auto-detect the format. So what we're doing is we're taking that archive and feeding it in through the external initRD loader. And the reason we do that is every time we change the root file system, we don't have to rebuild the kernel. Because if it's statically linked into the kernel, we'd have to rebuild the kernel, and that's slow. And then the last part, which I screwed up, there should not be a space there, is append. This is QEMU's for provide these extra arguments to the Linux kernel command line. What is the Linux kernel command line? There is another one of these. kernel.org/doc/D documentation is the online place for the documentation directory in the Linux kernel source code. Under the Linux kernel source, there's a D documentation directory with lots and lots of files in it. I've already shown you documentation, file systems, ramfs, rootfs, and initramfs.txt, which is the documentation on initramfs. Now let's look at, they moved it recently. It is now in, okay, they moved it between 4.9 and 4.10. It's in a different place now, but it's still in the old one here. It moved into a subdirectory, but it's the same file name. Kernel parameters is a very nice file that just lists all the keyword equals value names that you can provide on the kernel command line to tell it to do stuff. Again, as with the configuration symbols, there's lots and lots and lots of them, most of which aren't very interesting. The ones that you are required to provide are, well, the main one, and that's wrong too. If you're using a serial console, you're going to want to say console equals the device, the name of the serial device that you're using. You don't have to say /dev. If you do, it'll recognize it and chop it off. But you have to identify which serial device should the serial console attach to. Because otherwise, you won't get any console output. And then panic equals 1 here says, if the kernel panics, reboot after this many seconds rather than hanging. And remember, that will make QEMU exit. So that's a lot more convenient here. So we take this big invocation and we go, and this will die because on this machine I have the root file system in another place. But let's just use the one that I built a moment ago, which is that root.cpio.gz that we just did. So let's go back to here and go root.cpio.gz. And now, in a moment, we should get, come on, hello? Do I have a broken QEMU on this machine? All right. You're a much faster machine, but I'm going to go back to the one that I actually did the initial setup on, because this is silly. Oh! Yes, that would be wrong. That would be why. And it didn't make it far enough to panic, so it never tried to exit. QEMU system x86-64, yes. That's much happier. Thank you. So here are, you'll notice there's lots and lots of boot messages. What are you doing? Clock source switch to clock source TSC. Yes, I saw that. Come on, you should finish booting. Oh, do I have a weird version of QEMU on here?
You have another word relax.
Oh, yes, I do. Blah. It was booting asynchronously, so yeah. So it continued to spit console messages after the thing. So as I said, this is very simple to build and pretty much useless. We need to make the kernel smaller. We need to make user space bigger. Well, the next way to make user space bigger, what have I got in here? Is I have a copy of busybox checked out here. And what I'm going to do, it is config prefix. So I'm going to go make def config. Who here has not configured a Linux kernel? OK. We're going to get to configuring the Linux kernel, but busybox actually copied kernel configuration infrastructure. So if I go make menu config, I get an interactive configurator program where I can cursor up and cursor down, and I can hit enter to go into a menu, and I can hit space to select a symbol or deselect a symbol, or sometimes it'll cycle through *M and space, where the M means build this as a module rather than statically linking it into the kernel. And if you don't understand what modules are, just don't use them. Modules are a thing you level up to when you need them. It basically means that after the kernel has booted, you can tell it, here's an extra chunk of code using the insmod or modprobe program. Say, insert this module into the kernel. And you can also tell it, remove this module from the kernel, at which point it will hide it from you but not free up the memory. Unless you've configured the kernel in a way people usually don't and provide an extra flag that will from that point on mark your kernel as tainted, so that if you submit a bug report after doing it, the kernel developers will explicitly ignore you. Yeah, because removing bits from a running kernel is just not something that can ever quite be done safely, or at least they haven't convinced themselves that it has, and they don't want you to do that. But people like Red Hat with large amounts of money from corporations where the system should never be down even for maintenance, they love you to do that. So they'll argue with the kernel developers. But anyway, this menu config program is basically just a way of configuring stuff. And then when I'm done, do I want to save the new kernel configuration? In this case, no. Well, now if I go to busybox and busybox, make menu config, there is a similar menu config here, where, here's stuff that would be in the GNU core utils package that was completely re-implemented. Here's, do you want the DOS to Unix command? Do you want the df disk-free command? And they have a whole bunch of sub-things of, do you want it to have these features? And back when I was maintaining this sucker, I did a policy that there are a bunch of, make help on a lot of packages will actually provide, here's various make targets. That's a good thing to know. And you can then grep for the ones that have config in their names. Def config is the default configuration. You'll notice that we did the x86-64 def config over in the kernel land. Well, in busybox, make def config basically says, switch on everything that is sane. Don't switch on the weird debugging stuff. Don't switch on like the SE Linux stuff that won't build if you don't have the right headers installed. But if it's a feature, switch it on. Give me a configuration that includes pretty much everything we know how to do. So this is the biggest busybox you can get. And then you can go into make menu config and start switching stuff off to pare it down. There's usually two starting points with any menu config based thing. There's all no config and all yes config. All no config is basically if you went into menu config and switched off everything that could be switched off, this would be your config. All yes config is the opposite, switch on everything that you can switch on. And the reason that busybox def config is different than busybox all yes config is that in busybox all yes config is insane and switches on stuff that no sane human being would ever want. And usually, whatever your system is, it won't work. Because I mentioned weird debugging stuff. So make def config is a good starting point. So what I did is I did make def config, and then we compile it, which shouldn't take as long as the kernel did. And I don't know if this is a release version. This is a random git snapshot, but it should still work. I built it before. If you're going to deploy it, use a release version. OK, and then make help grep install, which has config prefix. So make config prefix equals, I can just do pwd is an environment variable that is my current directory / walrus, just some name that I know isn't already there. So I told it install into a directory that doesn't exist. And so it populated this new directory. Oh, yes. You know, my red-eye flight that I had to get up at 3:30 a.m. for was yesterday. You'd think I'd be recovered by now. That's why I got this. The drink that chases unicorns into the ocean. Ah, nasty stuff. Okay. So this popular directory, remember I said the older Linux RC name that nobody uses anymore? Well, busybox has been around for a while, and it hasn't necessarily cleaned out all of its old stuff. So what I do now is I do the same trick of find period, pipe it to cpio -h nuc oh, I never remember that part. I wrote the documentation on this so I wouldn't have to remember it. Yes, yes, yes. Duh. Okay. -o. All right. -o. Pipe it to gzip and root2.cpio.gz. And now what we do is we take our earlier kill QEMU system x86-64 and we cursor up and we tell it instead go to busybox root2.cpio.gz, and now we add one extra little thing, rd init equals bin sh. What I'm saying is, instead of looking for a file called init in initramfs, look for this file instead as your init program. The name rdinit dates back to when we were using RAM disks instead of ramfs, but it listens for both. So what that should say is do the same big, long, overcomplicated boot, and no, it didn't. Okay. And you know what I did wrong? I didn't statically link it. All right, let me explain more. Need more exposition. So what it did here is it failed to boot. It panicked at the end. And freeing unused kernel memory is the last thing it says before launching init. In this case, it's freeing 3 different chunks. Failed to execute /bin/sh, error -2. Error -2 in the case of the file is user include sm generic error-no-base.h if you know that. And eno-ent, -2 in this case, eno-ent, no such file or directory. But bin sh is there. Yes, but the dynamic linker wasn't. Because I forgot to statically link it, wherever it is, bin sh is a symlink to busybox. Busybox is a file that is dynamically linked. And it is looking for, the first thing it's going to look for is this file, which is the dynamic linker. That is the program it will actually execute, and then this program will be the first argument to that. It's kind of like when I have a shell script. It has # exclamation point and a path to the thing to actually run, and then the thing that you actually run gets this as an argument so that Perl or Python or the shell can interpret this script. Well, dynamically linked ELF binaries work the same way. They have a dynamic linker program that runs and then loads all these other libraries from the library search path into memory, links all the references out of this thing to them, and then jumps to its start. And what it was basically saying is this misleading error message, the no such file or directory, was saying the dynamic linker in this thing wasn't there. All it had was a number, and the number did say what the problem was, but it didn't say what file the problem was. So if you encounter that kind of thing, you learn to debug this kind of stuff. Okay, so what we do is we build again, and this time, make clean, I don't have to do a make clean, but I don't remember the way to tell it to. So LD flags equals -- static, make J8, yeah, right. And we build again. Ooh. And then when that's done, I can test that the busybox file is statically linked. While it's doing that, let me point you at a couple other interesting web pages. So, yeah?
What's the difference between RD init and regular init?
In current kernels, not as much. In current kernels, I believe that initramfs will fall back to looking at init equals. That went in like 4.6, 4.7 or something. It's fairly recent, it's within the past year. Init equals used to just tell the kernel what init to look for when it was mounting a block device on, stage 3, the root equals file back. After it couldn't find a statically linked initramfs, and then it couldn't find an external RD image, so it didn't have anything in initramfs or in initRD, then the third thing it would try to do was mount a block device, and init equals used to only apply to that block device. You needed the other argument to tell initramfs what init to look for. Okay? I think that has recently changed, so I could say init equals. And I'm using a 4.9 kernel, so we might as well try. Let's see, so that will have, okay. So what I was pointing you to here, let me finish the thought. I wrote a lot of documentation in that system that I have since stopped working on. But I did this one for 15 years, and I still answer questions about it. But Aboriginal Linux, our motto was we cross-compile so you don't have to, where it booted the smallest, simplest development environment capable of rebuilding itself under itself from source code and building Linux from scratch under the result. And that meant you could natively compile anything under QEMU that you wanted to without ever having to cross-compile again. Cross-compiling is very hard. I wrote documentation. I meant to hand this out to the group. I wrote an intro to cross-compiling that explains, basically what cross-compiling is and why cross-compiling is hard. This is very polite because this was written not to scare people away from cross-compiling. This was sort of, so you have to cross-compile. My sympathies. Here's how to do it. If you can avoid cross-compiling, try. Because cross-compiling is really, really nasty. You have two contexts. You have two sets of headers. The one for the system that you're building on and the one that for the system you're building for. You have two sets of libraries you're linking against. One for the system you're building on, one for the system you're building for. Most systems go configure, make, install. And configure asks questions about the system you're building on and uses them to apply to the system you're building for. And when they're two different systems, the whole of configure is asking the wrong questions. About half of cross-compiling is figuring out how to lie to autoconf or to just get it to stop. Because it's like, well, let me build a little test binary and run it to see what output it produces. Well, you can't when you're cross-compiling. It won't run on this system. That's sort of the point of cross-compiling. And your build system, if you are building something locally that generates a header file, a lot of times you will run a small C program to produce code or modify code that then gets compiled. So you need a native compiler, you need what's called a host compiler, and you need a target compiler to build for the target. And so you have two separate contexts and have to keep them separate. You have to prevent bits of your host system from leaking into your target system. And what you wind up doing is, just natively compiling on a bunch of different targets. It's like I tested it on ARM, I tested it on Spark, I tested it on PowerPC. I found slightly different bugs in each case, but that's okay. There's a linear number of them. Well, when you're cross-compiling, I tested cross-compiling from this system to that system, and I got slightly different bugs every from system. So it's hosts times targets. So you're testing attack surface is just exponentially larger. And then there's the fact that only about 2% of the developers will ever care about cross-compiling at all. Debian has over 40,000 packages in its repository. Maybe 1,000 of them have ever been cross-compiled on a good day with a tailwind. And so it's just, cross-compiling is a thing that can be done. But the point of this entire project was native compiling under emulation is so much easier. And then the trick I did was I fired up distcc and taught it to call out through QEMU's emulated network to the cross-compiler running on the host. So configure ran fine. There was one set of headers. The header information was pre-processed before distcc sends it out to the compile node. Linking ran fine because that happened inside the emulator. I could install the result into the system so that my dependency recognition, worked fine. But the heavy lifting of compilation was moved outside of the emulator to someplace that CPU was cheap and I had access to SMP. So that was a fun thing. I did it for a long time, and it's sort of out of scope here, but feel free to read about it. What I'm actually working on now is a project called MakeRoot, which basically, one of the things Aboriginal Linux did is it built its own cross toolchain and its own native toolchain. Well, there's a project out there now called Muscle Cross Make by the guy who does Muscle libc, Rich Felker, which is a toolchain builder that not only creates cross-compilers, but creates native compilers, which is the thing that I couldn't beat out of, BuildRoot will create cross-compilers. It doesn't want to create native compilers. CrossToolNG, it'll create cross-compilers. It doesn't want to create native compilers. Code Sorcery would give you cross-compilers. They wouldn't give you native compilers. There were a bunch of places I get cross-compilers from. But if I then wanted to build stuff in the resulting system, I didn't have a compiler I could install into the thing. I could fish them out of Debian. Debian has native compilers for all the targets it supports, but they depend on Debian. They're dynamically linked, not statically linked. So I would need glibc installed for like Super H and stuff like that. And it's like, Well, now I have a package that will actually give me the native compilers, which is why I started over and I went, I can be much, much simpler about building a thing. And what this is a shell script that builds a root file system, which I'll go through this in a little bit. After I go through configuring a kernel, I'll go through this as, here's how you make a simpler root file system. But it's a shell script that will basically populate one of these directories, you then CPIO up, and then run it out of initramfs, and that gives you a nice starting system. Once you have one of these things, if you want to repackage it as ext2 or repackage it as squashfs, there's a make squashfs utility you can read the man page of. I can walk you through how to do that too. Basically creating a file system for one of the other file formats is either run a utility like make squashfs or genext2fs that works like tar does. Here's a directory, here's the output file, it just puts it into the thing. Or what you can do is you can use a loopback device. Anybody here not know about loopback devices? Okay. Loopback devices, if you need to create a block device file system, you have to do it as root. You can, let's see, ddEIF equals dev 0, OF equals blah.img, BS equals, block size equals 1 meg, count equals, let's say, 256. So let's create a 256 megabyte, capital M, shouldn't have to care. So that created a 256 megabyte blah.img. And then I can format it. Yes. Whee! Come on. Come on. There we go. And then I can go mount-o loop blah.img. Need to create a directory for it. Mount-o loop blah.img subdir. And then there we go. And subdir is that file system. A loopback device is a special block device that creates, it basically is, it's another type of lens. Remember how I said ext2 is a lens you look at a block device through to make it look, like a directory full of files? Well, this driver lets you look at a file and make it look like a block device. It shows up as dev loop 0 or dev loop 1. There's a bunch of them. These days it dynamically creates more. There used to be a static number of them, kind of like PTYs. They're dynamically allocated now. They used to be statically allocated. They split the difference by statically allocating the first few and then dynamically adding more as you ask for them. And what you can actually do is you can do lo setup dev loop 0, which I believe by default will tell you what it's associated with. So if I say dev loop 1, it says it's not associated with anything, but dev loop 0 is associated with this thing. If what the mount command is doing behind the scenes is calling lo setup to associate file name with loop device, there's a man page on lo setup, if you want to know. And then when you unmount it, the unmount command recognizes, oh, this is a loopback device, and calls lo setup -d to deassociate that loopback device with that file. And the advantage of this is I can copy a file into here. That's 2.txt into subdir. And then I can unmount subdir, and then I can gzip blah.img, and I have just created a compressed ext2 image of 256 megabyte size. That's the basic procedure for if I want to create block device images. Now, this works for normal block devices. It doesn't work for flash devices. Flash devices aren't exactly block devices because the way flash works, normal block devices have a granularity of like 512 bytes, or these days 4K, and the file systems have a block size of like 4K. This is the size that they upgrade with. If your underlying device has an update granularity larger than the block size of a file system, bad things happen. Because if your flash, every time you write to the flash, it's updating a 128K chunk, and you think you're writing 4K sectors. So you have ext3 journaling, and it's like, right, we write these things into the journal, and then we update just this sector, and we haven't written anything before it, and we haven't written anything after it, so we don't need to keep track of that. And if we lose power in the middle of it, all we have to do is replay the journal, and that'll tell us, what changes we were in the middle of. And then when we try to remount it, oh, the entire directory is gone because that 4K was in the middle of 128K of directory, and all of it got zeroed and then didn't get written back because the power was interrupted, and oops, my flash file system is corrupted because I'm using a file system type that isn't aware of flash's erase granularity. This happens. It's a bad thing. So they have what's called log-structured file systems that are designed for use on flash, that the first thing they do is they do a special I/O control against the block device that says, what is your erase granularity? What is the update size and alignment and stuff? Where are your erase blocks? So that every time I update, I am updating an entire erase block. And they do things like they pack the data into the erase block so that they're not doing extra writes to, we only updated a little of this thing, so we don't want to erase and rewrite the whole thing. We want to save our writes and round robin around the disk because that's better for Flash because Flash wears out. So they work in a completely different way. And if you try to mount one on a normal block device or on a loopback device, it goes, I can't figure out what the erase block size is. That's part of the format of the file system. I fail. And it refuses to mount. So if you mount one of those, you have to provide, if you're faking it on something like a block device, these days I believe you can provide an extra -O option to tell the driver and pretend your erase block size is this size so I can make a Flash file system that I can then copy into Flash. But that's a whole area you now know you need to look it up, but I can't cover it in any reasonable detail here. OK, so meanwhile, going back to here, we have built. I opened a lot of windows, didn't I? I wonder which one is. OK, here we go. So did I install? No, I didn't. So make. I should still have it up here. Make. There we go. Oh. Did you have a question? OK. So we install into the thing now. And it's the same thing except statically linked. No, dynamically linked. Darn it.
You didn't recursively remove the Walrus string.
Yeah, it should have installed over it anyway. You want to try that? Yeah. I didn't actually do a make clean this time. Did you detect that I changed the C flags and you're rebuilding everything? OK. Statically linked. Woo! All right, let's do that install again. What are you compiling? I just built. Oh, you're going to rebuild the thing and I didn't do the C flags here. Yeah. I note that I haven't maintained this project since 2006. You can blame me for this, but I will complain. All right, so file, Walrus, bin, busybox, static, woo! And let's do the CPIO thing again, which should still be in the command history. And now let us go to wherever I had that kernel launch invocation. Too many open windows. Here we go. And let's try it now. Hey, all right. I have a shell prompt. So I have now made a simple to make kernel and root file system. The kernel is still 6.5 megs, containing, as you saw from the boot messages, lots and lots of stuff we don't need. And the root file system still has rather a lot of stuff we don't need. It's the biggest busybox you can make. And also, well, it doesn't have an init script. So I have to mount t proc make dir proc. I didn't make the directories. And then I should be able to if config. And nothing set up the network. We need an init script that actually does some stuff. So actually, I'll get to the kernel. Let me go to the root file system stuff first. This is that root file system builder I talked about. So let me walk you through what it does. You can, github.com/landley/makeroot, there's one script, makeroot, where you can basically just let me see if let me check out a fresh copy of it. Well, no, just. Do I have? No, I do not have it extensively locally modified here. Woot. January 31st, is that current? Let me see. Yes, OK. So the first thing it's building is, when I left busybox, I started over from scratch in a project called Toybox, because I felt I could do a better job. Toybox is now the standard command line of Android. I am attempting to turn Android into a self-hosting development environment. I'm using what I learned on Aboriginal Linux to basically make it so that what's installed by default on Android should be enough to build AOSP, let alone Linux from scratch, so that having an Android phone is sufficient to develop for Android. It's got USB on the end of it. If you plug it into a USB hub, you can add a USB keyboard, USB mouse, use Chromecast to put it on a big screen, and this is a gigahertz processor with at least half a gig of RAM. It's a reasonably powerful system, and if you plug it into USB, it's going to be charging itself. So I gave a talk about that here at 2013. The Android guys went basically sure, why not, and started merging my stuff. And that's taking up an awful lot of my time now. Oh. What I didn't do is I didn't tell it to use the current version of Toybox, but I'll just grab the one of the things I did is I made it so that if you have an extracted directory in the packages directory with the same name, it'll use that instead of extracting the tarball. It's 300-something line script, but it actually does a lot. So let me walk you through it. So it's building Toybox instead of busybox because I am migrating all my own stuff from busybox to Toybox. It's a somewhat cleaner implementation. If you saw the talk a couple of sessions ago on shrinking the Linux kernel, he was comparing Toybox to busybox. The really fundamental difference, the reason that Android can use it and couldn't use busybox, even though busybox predates, busybox is older than Android, and you're not going to wait for them to start shipping it. They're not shipping it for a reason, is that they have a no GPL in user space policy. GPL v3 happened about the same time that Android did, and they responded by throwing out the GPL v2 baby with the GPL v3 bathwater. Now that there's no such thing as the GPL anymore, and you have warring camps that can't, the Linux kernel and Samba can't share code, even though they implement two ends of the same protocol, and each has to police their submissions to make sure that they didn't get code from the other one because that would be incompatible and they'd get sued. It's like Android just went, nope, opting out, and they rewrote. They rewrote their Bluetooth daemon. They threw away the one they had that was GPL and wrote one that's Apache licensed. They're slowly going through and moving that. So Toybox is under a public domain equivalent license that looks like a BSD license to make the lawyers happy. And, that's why they can merge it. OK, so I did just build the thing. And what that did is that created a directory called root that has a bunch of stuff. And in the build directory, it created a root.cpio.gz. And this is a mix of Toybox and busybox. You could use just busybox, but as I said, my own personal development, I am migrating from one to the other. I'm only using busybox for the commands I haven't implemented a good enough version of in Toybox yet. So walking you through what this does, this is the script on GitHub. It starts if you don't run it with if you run it with unknown commands, it prints out a help message. It figures out if you've set the environment variable cross-compile. If so, that is what cross-compiler to use. That says I'm not building it for the host system, I'm building it for ARM or PowerPC or whatever the cross-compiler is. So it figures out a couple of things from that, and it makes sure that it can actually run the cross-compiler, because if you point it at a cross-compile, compiler that isn't in your path, it'll go, no. Those directory names I mentioned above, you can replace them if you want to. It checks to make sure that you can build static binaries, because it turns out on things like Fedora, unless you install the package that contains libc.a, it doesn't install the static libraries by default. So you have to install an extra package in order to be able to link stuff statically. When you install a toolchain, it can only do stuff dynamically, because Ulrich Drepper hated static linking. And even though he left to go work at the Bank of Evil, Goldman Sachs, they haven't undone all of the damage. Static linking is very useful. You'll notice I hadn't copied the shared libraries into the root file system. I could run the LDD command to see what shared libraries do I need and copy them. And then remember to run LDD against those libraries because libraries can link against other libraries. But that's a lot of work up to that. The simplest Linux system, as it says in the title of the presentation, is not going to be dynamically linked because dynamic linking adds complexity. Statically linking, dynamic linking is worth it once you have reached enough different files sharing the same libraries that you're saving enough memory to care. And that won't be for a while. Okay, so this is a thing that basically just extracts a tarball into a working directory, and it checks to see if there is an extracted version, and it will use that instead. It's only a few lines. You can read that. So, and then cleanup is the one that deletes it afterwards. This is basically tar extract, and this is rm-rf. Only they're kind of fancy versions. But every time you see that, one of them is tar extract. This does a wget of the source tarballs from this URL and checks the SHA1 sum. So these are the toybox and busybox packages we will be building. And then the first thing it does is it sees if there's an airlock directory that contains the toybox binary. Because I mentioned that when you are cross-compiling, it's easy for bits of the host system to leak into the target system. And you have that combinatorial problem where it built slightly different on Ubuntu than it did on Red Hat, than it did on this thing. And instead of one set of things to test, it's one for each target. So it's number of hosts times number of targets. And that is going to get out of hand, and you will have stuff that you haven't tested. Well, the way I solve that is I spent years making sure that busybox provided tools you could build a whole system with. And these days I'm doing the same with toybox. Every tool that is in toybox defconfig is good enough to build a system with. Not all the tools are there, but the ones that are there, my sed can actually run autoconf, that kind of thing. So what I do is I build toybox, install it into a directory, and then I have a list of files I need to copy out of the host system because toybox doesn't implement a reasonable version. And there will always be a few because I don't include a compiler. So I'm copying GCC, I'm symlinking to the host GCC, I'm symlinking to the host binutils in this directory of commands. And then I set the path to just that directory. And this is called the airlock step, where once I've done this, I'm using this little tiny system I built to provide a known build environment, to isolate against variations in the host system. Now, Aboriginal Linux was doing a whole lot more sanitization. It had a whitelist of environment variables, where if it wasn't one of these recognized environment variables, it would unset it. And it was doing a lot more cleansing and stuff. And 95% of the time, you don't need to worry about that. So this is a little more than the 80-20 thing. This is like the 90% that gets you 95% of the thing. So this is creating an airlock step, which is strictly speaking optional, but it means that I'm building in a known environment. I then, this is basically just dependency checking because, in case I don't need to rebuild stuff. Skip that step. Then what this does is this creates the directory layout. This is doing a make dir of all the standard directories in one line. This is pretty much the directories that packages expect to be in. And with this set of directories, I can install all the Linux from scratch packages. Linux from scratch is an online book that tells you how to create a very large, very complicated, about 110 megabyte system using conventional GNU packages. But it's the base of most OS versions. It's nothing remotely like the embedded world uses. And as I said, I spent many years making it so that a megabyte and change of busybox could replace 100 megabytes of GNU packages. But that is the old reference build that I use. Because if you want to use the big version of sed, you can. Mine should be a drop-in replacement for it, but in order to ensure that it's a drop-in replacement, I need to test against the old one. And I need to test that it can build the old one in case I am missing anything. So, there's an etc directory, a tmp, proc, sys, dev, home, mnt, root, and then under user, there's bin, sbin, and lib, and then there's a directory var. And these are pretty much the directories that Linux expects to be there. There is a standard called the Linux Standard Base, LSB, that unfortunately the Linux Foundation took it over. The Linux Foundation was formed when when two black holes of bureaucracy combined to form Voltron of bureaucracy. And one of those was the Free Standards Group, the other one was OSDL. And when they combined, the focus shifted from maintaining this standard to asking donors for money. And unfortunately, what this meant is that the Linux standard base was so badly maintained that a year or so back, Debian, when the 5.0 release came out, threw up its hands and said, we're done, we're not paying any attention to this standard anymore. Which is kind of sad because there should be a standard for this stuff. So there's still 4.1, LSB 4.1, and it does describe the layout of these things. Etc directory is where a bunch of config files traditionally live. Temp was the directory that Unix used for temporary files. Proc is where you mount procfs, sys is where you mount sysfs. Those are two synthetic file systems that let you give you an API to play with the kernel so that PS can see what processes are available and insmod can see what hardware is available and stuff like that. Dev is the directory that the device nodes go in. I mentioned that the serial console device is one of the devices in dev. Dev lo setup. Dev loop 0 when I was showing loopback devices. Home is the directory under which the user accounts live. MNT is a directory for additional mounts. That's the traditional name for it. Modern systems added one called media that does the same thing, but they liked it. Root is the home directory of the root user. This is fallout from the days when home used to be on its own partition a lot. And in case you hadn't, if you ever trashed that partition, it would give and had to log in as root to administer the system, it would give the root user, somewhere to have his files. User bin, sbin, and lib actually exist because Ken Thompson and Dennis Ritchie on their original PDP 11 in 1971 filled up their first disk. Their root disk was a 0.5 megabyte, very fast disk, and then they had what was called an RK05 disk pack, which was 2.5 megabytes of external space, basically like a USB disk today. Slower but much larger. And when they filled up their root partition, they leaked it into the user directory where they had the user accounts. And then when they got a second expansion disk, they moved all the user accounts to the new disk, and they called that one home. And they left the user directory to be eaten by the operating system. And then people retconned all sorts of rationales for this, but no, that's why it happened. And these days, when I'm making a system, you will notice I just symlink user bin to bin, user sbin to sbin, and user lib to lib. So, there's a bin, an sbin, and a lib at the top directory that I just symlink to the second copy of them, collapse them together because I don't care, it doesn't matter. But I researched why they did this in the first place, and Dennis Ritchie wrote it up as a historical anecdote, and I went, oh, that's why they did it. Now I know that we don't need to do it anymore. A lot of this researching why we do things in the first place, if you drill down into it, a lot of times you can figure out it's okay to do it differently, and it's okay not to do it at all once you understand why it was there. So that's an example of that. And then the var directory was it was a place to put things that should persist across reboots but should be writable, because etc could be in a read-only directory. So config files versus dynamic config files. So those are basically the directories it expects to be there, and you can just copy this snippet right out of my thing or just run this file. Then I create an init program. Now you'll notice I said, init is PID1. It is the program you run when the system first comes up. And I actually wrote up a little things I probably won't have time to cover, but should. Okay, so init is weird, and I wrote down why, and yeah, these are a bunch of different examples of types of init you may encounter. Using binsh as init, you've seen me do that. Your app, the Hello World, was an example of that, but a lot of Internet of Things thing will just run, their init as PID1. Here is a shell script running as init, and then at the end it execs another program. I wrote one called oneit. There's system 5 init, which was the conventional one everybody was using 10 years ago. Then Android uses its own init program. These days there's a horrible one called systemd. And then there's others like Upstart and OpenRC when people were trying to move beyond. The main problem with System 5 init is it predated the widespread use of SMP, so it brought the system up in a single-threaded manner. And people wanted to parallelize the init to bring the system up faster, and they couldn't quite agree on that because, well, this has to come up after the network interface comes up, so suddenly we have a dependency resolver where everything has to know what else it depends on, and people wrote up a lot of different things, and Red Hat basically shouted everybody down by having more money. Okay, so PID1, the first process that Linux launches, is special. And what's special about it is, to start with, it has no parent. It is launched directly by the kernel. If it ever exits, the kernel will panic. You saw that kernel panic earlier of, we couldn't find init because it was, or we couldn't run init because it was dynamically linked. So we got a panic message, and then QEMU exited and otherwise would have rebooted the system. Because init should never exit. Init has most signals blocked. Specifically, the way they implement that, not exactly, but you can think of it as sig default is sig ignore for init, where if you get a signal, the default handler for it will ignore it rather than killing the program. And if a program's parent process dies, so that you have an orphaned child that when it exits, it wants to send sig child to somebody to notify it of its exit code, but its parent has gone away, it will be reparented to init. Init is the reaper of orphan children. Okay, so init does a lot of things. If you run init equals /bin/sh, your system will accumulate zombies if your shell does not know to listen for sig child, which most of them don't. There is actually a workaround. If you set sig child to sig ignore in the signal handler, tell it, instead of having a signal handler, just set it to sig ignore, sig child will be delivered, and the fact that it was ignored is fine, and then the child can exit. So when you are running an init program, if you're not going to handle sig child, set the signal handler to sig ignore. And you have to actually do that explicitly because the default one being like sig ignore isn't good enough in that case. So yeah. And another thing is, for example, init can't reboot the system because the reboot system call exits your process, so the kernel will panic before rebooting. So you have to fork a child, have it call reboot, and then you hang and wait. Yes, I mentioned that I wrote oneit. Oneit is a tiny little init program. It's in Toybox. You can find it on the busybox mailing list way back when, but they didn't merge it, where it does just the basic setup. Another thing about init is that it inherits file handle 0, file handle 1, file handle 2, pointing to dev console. It starts with a standard in, standard out, and standard error, pointing to whichever dev console you had on initramfs. If you didn't have an initramfs, or if you created an initramfs but didn't add a dev console to it, which you'll notice we haven't in any of the ones we've done so far, those opens will fail. And your standard in, standard out, and standard error of init will be closed. Meaning, anything you write will be ignored. And if you try to do that as a shell prompt, if you try to then exec binsh, it will exit immediately because it has no input to read from and no output to write to, and it basically gets a sig pipe and goes, nope. So what this init script does, this init script, we start with # bin sh. We then set a home directory and set a path because we didn't necessarily inherit one. Our environment is mostly blank. So if we want some basic environment variables that you just sort of expect to be there, we have to set them ourselves. We mount proc on proc, we mount sysfs on sys. The reason that it's doing this is I sometimes use this init script to change root into a directory. And when you change root into a directory, the system may already have some stuff there. So that's why I'm checking if they're already mounted. Is just for change root, it won't be in your systems. I then mount dev tempfs. Dev tempfs is a file system that was added a few years ago that automatically populates the dev directory with all the devices that are there, so you don't need something like udev or systemd to do it. You don't need a daemon listening for hot plug events and creating device nodes. The kernel can do it for you. And it took several years to browbeat Greg Crowe-Hartman and company into going, the kernel can really do this for you, but what names will we use? Okay, you notice how under sysfs, sys class, like, mem, there are names? Why don't you use these names? And eventually they went, all right, we'll use those names. They are unique. And it's like, yeah, so you get a set of devices from dev tempfs. And then dev pts is the pseudo terminals. If you use the new PTY format that automatically allocates them rather than the statically linked ones from way back when, that requires a file system to, every time you create one, it shows up in this directory. So that's where it expects it. So yeah, that does amount of dev pts, amount of dev tempfs, amount of sysfs, and amount of proc. It then does an if config of eth0 and a route add default gateway for QEMU. If you are using QEMU's emulated network, this is the address that if you ran DHCP, this is the address it would give you, and this is the gateway that will talk to the outside world through its basically faked IP masquerading that it does. And then I attempt to set the date in case I am emulating a system that doesn't have a persistent clock. Because some ARM or SH boards or stuff like that, it's like this system doesn't have a clock, so the kernel doesn't know what to set the clock to. So I can do it, once I brought up the virtual network, I can do a transaction with the host that says, hey, what time is it? And get that set up. I then figure out when the kernel command line is available. I think this is actually the, this is the kernel I just built. So this is the emulated system, actually, that is still running under QEMU. And proc command line, this is the command line that I fed in. You may remember that from the QEMU command line. So in procfs, I can see what my command line is. And what I did here was I ran sed against proc cmd line to see if there's a command line argument. If so, I figure out what device it is. And the reason I do that is, remember that standard in, standard out, and standard error that init inherited, go to /dev/console? Well, dev console is a device that is an alias for whatever actual console device you're using to talk to the outside world, but it does not provide a controlling TTY. So if I hit Control-C, it doesn't send a signal to my program. And if I run like ping, that just endlessly pings stuff and doesn't exit, and I'm going Control-C, 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 and it's ignoring me, and I'm going, right, I have to reboot my emulator because I screwed up. Well, what oneit does is it closes the standard in, standard out, and standard error that it inherited and opens the ones from the actual console device, the serial device, that does provide a controlling TTY. So that if I'm connected to that one and I hit Control-C, it sends the program a signal. Okay, so that's why I'm doing that thing with the console. You don't necessarily have to do that in your thing if you don't expect to have a command line running as PID1. Your init will also do the proper setup to that thing if you run sys5 init or something like that. But I'm doing that here because I'm trying to be simple. And then I figure out, okay, what program do I run next? By default, I just run bin sh, but I can set the environment variable handoff in all caps. One fun little thing about this is, let's see. Any unrecognized keyword equals value argument on the kernel command line, it will set as an environment variable. So I can set any environment variable I want to tell my init script to do stuff on the QEMU command line. So that's just a fun little thing. Now notice I had to put that before the rd init line because init equals or rd init equals, it will think that it's an argument to sh. Okay? Once you get to that point, everything else becomes an argument to sh, so it would have to, it does have a positioning dependency. All right, so getting back to this script. So I create my init script, and here is the EOF of the here document. If you know shell programming, I just wrote this out as a here document so that the contents of the script could be in the script. And then I change mod plus exit, because if it can't execute the init, it won't run, and you can't run a shell script unless it has the executable bit set. I then write out an etc password file to say these are the two users that are on the system. And this is in the format that etc password has been in forever. And I write out an etc group file. I did not write out shadow files, so there's no passwords associated with this. I can't log in as any of these users. But SU, if you're switching user from root, doesn't care. And I could have set up a shadow thing, but then what passwords would I assign to them? It's like I just didn't bother. But this lets them know UID 0 is root, which UID 0 is always root, but this lets it know that the name root goes with that. And if I log in as root, my default shell should be bin sh, and my home directory should be here. And then I created a guest account to be UID 500, and I told it, here's your home directory, here's the shell to run. That's just what the etc password format is. I think there's a man page on it. And then I wrote nameserver 8.8.8.8 into etc resolve.conf. The file /etc/resolve.conf is the file that the C library reads every time you attempt to do a DNS lookup. It goes, where are my name servers? 8.8.8.8 is the IP of the Google DNS pool. So I don't actually have to even put in a second one. You're supposed to have fallback servers, but that's a pool of 30-something machines around the world that it does the automatic magic routing to the closest one through the weird backbone stuff. And that basically means that should all, if I can get out to the net, that's a DNS server that should be up barring nuclear war. And even then, maybe. So then, so those were actually the directories I created and the configuration files I added to give me a basic system where playing around on a shell prompt, if I do ls-l, it should give me usernames for the files, at least the ones belonging to root and group, sort of thing. Then I build and install Toybox, which, it's only this. And the only reason it's weird is, I did a make, setup for is the thing that's basically a tar extract to the tarball. Make def config, just like busybox. I then changed one of the symbols because the muscle libc maintainer and I have this long-standing disagreement about how noMMU should be configured. If you're not using a noMMU system, this does not apply to you at all, and I've actually updated that, but I haven't pushed it to the repository yet, so it only does it for noMMU systems. If you care about noMMU, stay after. We don't have time, but I've done a lot with them. I mentioned that ELF is essentially an archive format for binary data. Well, there's a slightly upgraded version called fdpic that annotates it with slightly more data. And the reason for this is NoMMU systems can't have two processes using the same address space to see different things because it doesn't have a memory management unit. It can't remap them. It can sometimes have, low watermarks and high watermarks where if you access memory outside of this window, you'll get a seg fault. But if you can access that address, you see the same thing for every process. Meaning, if your ELF thing wants to be loaded at address hex 1000, and you have two instances of it running, you can't. Because the second instance would need to load at the same address as the first instance, and they would get sad. And the way most ELF programs are linked, there's like 4 interesting segments. There's the code segment, the data segment, the BSS, and the other one. I'll think about it as soon as I stop trying. But the problem is they're all put right after each other in memory. And the addresses of them, this piece of machine code will go where I am, or the start of this, the start of the program plus this many bytes for the data, or for BSS is the, RO data is the other one. There's one code segment and 3 data segments, basically. One of the data segments is for data that you can, that starts initialized to a value, but that you can then modify it afterwards. It's basically your global variables that are initialized to a value. BSS is for your global variables that are initialized to 0, so their contents don't actually have to be stored in the ELF thing. It basically maps a segment of memory there that isn't backed by the file and then goes, have at. And then the RO data is the stuff that's initialized to a value, but then if you try to write to it, you will get a seg fault because it is not writable. And they're basically all glued together in ELF as one big contiguous chunk of memory. What FDPIC does is it says, these are now 4 distinct chunks of memory, load them wherever you can fit, and that means you can share the code segment with other programs that think they've loaded this. And it's a PIC, position independent code. Normally we only link libraries that way, where we say we have saved in a register or saved in some global thing that either ties up a register or causes an extra indirect load to slow your assembly down. But that means that wherever, it can be loaded at different starting addresses. And that means if you have shared libraries, well, each shared library doesn't magically know what all the other shared libraries you have running are, so they can't, at compile time, pick a unique memory allocation to be, so they have to be relocatable, because they could be used in combination with who knows what other libraries. Well, what they did is PI, position-independent executables, are executables built as PIC, so that they can be relocated. And the security guys love this, because that way, if you try to exploit it, using an absolute address, and it's loaded at a random location each time you load, it's harder to exploit. Well, the NoMMU guys love this, because it's like, I can have 3 instances of this loaded at different locations, and they don't, it's not going to conflict with other programs that think they're using the same thing. But what FDPIC lets you do is it lets you say, okay, the read-only section can be shared with other instances of the program. The code section can be shared with other instances of the program. The data section and BSS, you need your own instances of, because you're going to write to that data. So these 2 are shared wherever they can fit. These 2 are unique wherever they can fit. However, if your memory is fragmented, you can't use the MMU to collate it, but you can fit it into smaller chunks because we've broken the program into 4 different pieces that can load wherever you can fit them. FDPIC is much, much nicer for NoMMU systems. But it means you need a different kind of program loader. So when you build the program, you need to produce a different output format. So again, went off on a tangent. But anyway, that me arguing with the muscle libc maintainer, yeah. So anyway, it does a build, statically linking, and then it does an install, and then cleanup is that rm-rf thing. And then this is a busybox install where I did something called mini-config. And the last little bit I'm going to get to, and I think I'm going over time probably, but the last little bit I'm going to get to is configuring, drilling down into the kernel config. This is the same format as the kernel config. What I did is instead of a def config busybox, I told it, these are the symbols I want. Only these symbols. Start with all no config, and there's a bunch of them, but this is less than 100 symbols, and busybox has hundreds and hundreds of symbols. A full config file for busybox, which I just built, is 1,097 lines. It ends on line 261, and it started on line 191. So 150 symbols instead of 1,000 and stuff. And that's for selecting, rather a lot of stuff. And what this is a format called miniconfig, which I did write up documentation on once. Here. I tried to send this upstream to the kernel of documentation on how to do it. You'll notice this was 2005. I resubmitted it again a year later to see if they'd changed their minds, and nope, a bunch of people are using this. Documentation on it is not submitted upstream to the kernel. If you ever think about Linux kernel stuff, oh, well, any interesting idea immediately gets implemented and done by the vast hordes of kernel developers, I will point you at the fact that the squashfs developer spent something like 7 years attempting to merge squashfs into the kernel. He took a year off to full-time push it upstream into the kernel after it was already in Red Hat SUSE, Debian, Gentoo, and everything else. It had been merged everywhere, and the kernel developers wouldn't take it. I spent something like 7 years getting Perl removed from the kernel build environment. From the first, wouldn't it be a good idea to use tempfs for initramfs, from me first mentioning that on the mailing list of, is anybody working on this, to me actually sitting down and doing it was something like 9 years. Okay, so yeah, the normal state of things is for somebody to do it off in a corner and then it's abandoned and it never goes upstream into the kernel. If, browbeating all these developers for, you implemented stuff for your company and you've been using it in-house for years, but it isn't upstream into the kernel, that's actually fairly normal. It's sad, but it's normal. So, before that tangent, I was attempting to explain, what was I attempting to explain? I closed the window. I was attempting to explain miniconfig, where I actually did documentation describing, all sorts of stuff about miniconfig, but I will walk you through it right now. Basically what you do is you have keyword equals value config symbols like this. In the same format they appear in the config file. But the question you ask yourself is, if I start with make all no config in the Linux kernel and busybox and anything that's using menu config, and I go, okay, I've switched everything off, now I want to pull up that menu config tool, and I have a checklist written down of look for this symbol and switch it on. And every time I do so, there's a dependency resolver that may switch on other symbols for me or change their values or whatever. Well, that runs every time I poke a symbol in menu config, switch it on or switch it off. It may have fallout with other symbols in the kernel, but I don't really care. All I care about is I started with all no config, and then I went down my checklist switching on these symbols, and then I saved the result and I built it. I know how to do that by hand. Can I automate this process? And yes, you can. That's exactly what miniconfig does. And the magic line here is make all no config, kconfig underscore all config equals the name of the file containing all these symbols. It's a horrible name. A large part of what that patch I had from many years ago was having a make miniconfig target that, among other things, would tell you if you tried to set a symbol that didn't exist. Instead of silently ignoring it, it would go, oops, error, you screwed up. That kind of thing. And there was bike shedding from a guy named Roman Zippel, and even though he's not there anymore, tangent. So this is a fairly useful technique for configuring busybox a lot more, concisely. And it used it set it as an environment variable, not on the command line. Make is terrible. I'm sorry, people give Python guff about the significant white space and totally ignore the fact that make requires tabs, not spaces, in a lot of places. It's like, no, it combines imperative and declarative code in the same context where you have to care what order things happen in but have no control over it. It's like, no. Tangent. There's a whole rant on there. Configure, make, and make install all kind of need to be replaced. It's just nobody can really agree on. Well, I already went into the whole autoconf is, totally does not work with cross-compiling, and half the things it's checking for are specified by POSIX anyway, and if your build environment isn't POSIX, fix your build environment. And make install, of course, has no idea what a package manager is. So, things. Anyway, but meanwhile, we do configure, make, and make install. And config prefix just tells it where to install. And I'm installing the unstripped version in case I want to run GDB against it or something. And then this was my attempt to copy the dynamic libraries out of the cross-compiler onto the system to give the option of dynamically linking. And just ignore this entire section because it doesn't work. You can actually see that it's my second attempt. And the problem is I can get it easily to work with any one cross-compiler. Getting it to work with all cross-compilers, which may be using different C libraries, there's a lot of testing there. It's on my to-do list. So just ignore the thing about trying to make that work. And then if I want to build additional packages, I have a second example here that, what if I want to cross-compile more stuff? Well, here's cross-compiling, zlib and dropbear and installing those into the system. Here's just examples of using the same infrastructure to do that with different packages in case you want to cross-compile more stuff. And then at the very end, you may have noticed I kept pulling up this file to look at the end where it's like, and here's the invocation to turn that into a cpio.gz file. So that is what this build script does. And if you feed it one of the muscle cross-make tool chains, which I've been talking to Rich Felker, he and I actually work together, to try to get him to do binary releases so I could just point you at a URL of download the binary of the pre-built toolchain, extract it, add it to your path, and then follow along building the thing. And it's not up yet because he's been really, really busy. And I'm not hosting it anywhere because it's GPL v3 and I don't want to get any of that on me. I launched the first GPL enforcement suits that actually wound up in court suing people back when I was busybox maintainer. I know a whole lot more about GPL enforcement than any sane person would ever want to. And after a year of empirically going through and proving that none of these companies that were shipping busybox binaries had any code we wanted, not adding one line of code to the busybox repository after looking at a whole bunch of source tree dumps, I basically went, I don't want to go there, and I really don't. But it made me a lot more careful about license compliance stuff because you can't spend a whole lot of time dealing with legal stuff without being really careful to make sure you don't have to again. Okay, so that is an example of building a simple root file system, but building a simple kernel, defconfig was terrible. So let's walk through real quick because we're short on time. Let's walk through kernel building. So I showed you the start of this file before. Let's see, configure creates a config file. I haven't really had time to talk about device trees, but when the kernel boots, the bootloader, there's actually two bootloader stages. On real hardware, you have a bootloader stage 1 that does 2 minutes, lovely, okay. Ask me afterwards. The real hardware does things that QEMU doesn't have to. So QEMU is a built-in bootloader. We've just been using that and explain it now. So we start with all no config. And in order to do a standard x86 system, these are, in theory, the three symbols you need. What board am I using? And where is my serial console? So I set these three symbols. I then do the make. I then boot it. And I get no output. And the reason I get no output is that printf is switched off. Why is printf switched off? Because the symbol config embedded was broken by this commit, which was really stupid special case nonsense that says when all no config happens, switch this symbol on, which results in opening a menu so that a lot more symbols can be switched off. And this winds up switching off printf. So what you actually do is you do a special commit. Oops. So you have a line that looks like this: config embedded is not set, which ordinarily, which is how you tell .config a symbol is switched off. Yes, # means a comment, but this special comment is functional. So we add this line, and then we get output, but it says no file system could mount root. So we have to tell it to enable the check for external initrd, which are these two symbols. And then it says it couldn't execute bin.sh. So I have to basically switch on config bin format elf so it knows how to read an elf binary. And then I get to the point where it reads hello world. In order to be able to do a shell script, I have to switch on config bin format script. And then I can run my init script, except it can't mount devtempfs. So I have to switch on two symbols in order to get the file system that gives me the dev directory. And I could go into more, but basically this is the kind of thing that, the minimal set of symbols that I was using for each target back in 4.3. Let me github.com. Landley. Back when I was doing Aboriginal Linux, the set of symbols that I used for each target was in the targets directory. There were a bunch of things like, here's the one for ARMv5. In order to boot a system, I needed to know what arch equals value to tell the kernel when I built, what path the resulting bootable file would show up at. That's for building GCC. You don't have to care about that. What console value to feed it, because which console device am I using? And then here is here's the symbols I added just for this architecture for this board and the set of devices on this board. And here was the QEMU invocation I would use to load it. And that set of symbols was actually added to base config Linux, which has more than you actually need. But these were the common symbols that I would set on all the targets. So you can actually read through and see what those symbols are. You don't need a lot of these. And if I had a little more time, I'd go through here's the list of the ones you need. But unfortunately, I am over time. I can probably take one or two questions.
No.
I cannot?
Please not, Rob.
OK. Oh, sorry. Somebody needs the room. I'm sorry. Ask me afterward.